Hi. In this video we are about to see the packing fraction for simple cubic crystal structure, and what you see here is the model of a simple cubic. Well, here it shows that an atom's 1/8 of its content, 1/8 of the atomic content in each corner. In all corners it is 1/8 of an atom. So we can start the derivation. It is a simple cubic structure. It's a simple cubic structure. That means a unit cell or a square box or a cube. So I put a figure to show that it is a cube. Say this is the XYZ axis. X-axis, Y-axis and Z-axis, and in each corner 1/8 of an atom is present. So totally there are 8 corners, and in each corner 1/8 of an atom. So 1/8 of an atom. So one atom inside a unit cell. Now simple cubic crystal structure has a lattice parameters of A is equal to B, which is equal to C, and alpha, beta, gamma all 90 degrees. So in this figure, this is A, and in Y-axis it is B, and Z-axis it is C, and the angles are all 90 degrees each. So the condition is for simple cubic. So this is the condition for simple cubic. So when it comes to packing fraction calculation, packing fraction is the volume of atoms present inside the unit cell divided by the volume of the unit cell. So I represent it with a small v divided by capital V. Volume of the unit cell is capital V, and the atomic content present inside the unit cell, volume of the atoms present inside the unit cell, is represented in small v. So to get that packing factor, in this case it is one atom inside, so it is a spherical shaped object, so 4/3 pi r cube, one atom's volume divided by volume of the unit cell. Volume of the unit cell is A cube. We have seen now it is A, B, C, everything is equal, say which is equal to A. So volume of the unit cell is A cube. Now in this equation, what we are about to do is we are about to put a substitution. So before that, let me mark this as, say, equation number 1. The substitution that is about to be done is for, say, R. So I do it in advance. 4/3 pi R is substituted with A by 2 cube divided by A cube. That is packing fraction. So A cube is here, A cube is here, and this is 2 cube. So the remaining things are 4 by 3 into 3.14 divided by 8. So that makes it 0.52. Let's see it as 0.52, or it is 52%. 0.52 or 52% is the packing factor for simple cubic. Well, in this, how I have obtained as R is equal to A by 2. Let us see it in this following description. Let's come back to this model. Here the lattice constant, this is A, and vertical height is also A, P, which is equal to A, and this is also, C is also equal to A. Now in this figure I am about to put the model that I am seeing now. See here, I am putting a unit cell. As shown. So whatever I see here, I have marked it here. Say this is one side view, and the extension is outside. So this is atomic radius R from here to here. Another atomic radius is R, and the entire length from here to here, it is a lattice constant A. So what I can mark is 2R, 2 times radius is lattice constant A. So atomic radius R is equal to lattice constant divided by two. R is equal to A divided by 2. So this is equation A, and this is what we have substituted in our previous case. See, this R is equal to A by 2, we have substituted in the packing factor equation and obtained this 0.52 or 52%. Since we are getting only 52% of the atomic content packed inside the simple cubic crystal structure, we call it as a loosely packed crystal structure. It is a loosely packed crystal structure. That means only 52% is packed and remaining 48% is vacant. Well, so this is about simple cubic. Let's see one more detail about simple cubic, the coordination number. Coming back to this figure, it shows that atoms are present in each corner of this unit cell. Now considering this point, which happens to be the origin, and the atom present in the origin we are considering now. The number of nearest equidistant neighbors is called coordination number. So with respect to the atom in the origin point here, it has neighbors over here in the same line in the x-axis. This atom in the next corner in the x-axis, it is a neighbor. So in the model of we can find, say this atom means its neighbor is here, so it is touching it, and the next neighbor is over this corner. 2, it is in y-axis, and similarly in z-axis. When the next adjacent unit cells are placed, that comes in the opposite axis. Say if the x-axis is x100, it comes as x dash, y-axis as y dash, and z-axis as z dash. So just like in the x-axis there is an atom in the x dash, in the y-axis there is an atom, y dash axis atom is also a neighbor to it, and similarly in z-axis, z dash axis, an atom is neighbor to this. So in x, y, z axis 3 atoms are neighbors, in x dash, y dash and z dash axis also 3 neighbors. So totally 6 is the coordination number for simple figure. So when I want to put a simple figure to represent that, so what I can do is I mark in this manner. Say I can put a simple unit cell figure, and with respect to this atom, this is neighbor, 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 x-axis, x dash. So here there is a neighbor. So it is y-axis. So in y dash there is a neighbor, and here it is z-axis. Here there is a neighbor in z-axis. In z dash there is a neighbor inside. So totally coordination number is 6 for simple cubic. Thanks for watching.